Okay, so on this one, we have three charges. You had to know a triangle was coming. At three separate corners of a triangle, all the charges are equal, and they're equally spaced apart. So D is the same for all. The only way for this to happen is if all of these angles are 60 degrees. It's an equilateral triangle. So we want to calculate the net force that each part of our charge is experiencing from the other two. So to do that, we're just going to break it into pieces, and remember that Coulomb's law is KQ1, Q2, or in this case, whatever pieces they are, over r squared, over the distance squared. So we have the distance for each one, so this will be d squared, and these two charges are the same, so we can just call this q, but we'll go ahead and label them 1, 2, and 1, 3. We'll get to 2 and 3 after we do 1 and 2, so you can kind of see the pattern first. But notice, while we get the force, that doesn't give us the components to add up our forces experienced by each piece. So what we'll be getting is a force that is resultant on each side. Ooh. So that should be a clue that once we calculate these forces, we're going to need, let's see, we'll call this 2, 3, 1, 3, and 1, 2. We're going to need to break them down into their pieces. Therefore, all that practice that we've had on decomposing vectors. Make that light a little bit better. So let's start with 1, 2. Yeah, let's start with 1, 2. First thing, well, no, we'll just do this. We'll go force 1, 2 equals K Q squared, because they're the same, over D squared. Well, you're probably thinking, well, why are we going to go ahead and do that for everything? We're not. So we'll start there. We know that each distance between here and here and here and here is the same, so these forces are the same, but we still need our components. To do that, we're going to pretend like I drew a good triangle with straight lines. We're going to look and see, okay, remember cosine and sine, so starting from Q2, the adjacent side will give us our x component, and we'll notice that it's in the negative x direction. I've split my axes here, so this would be positive x and negative x, and down here would be negative y, and up here would be positive y. So in components, it would be negative k, because it's the negative x, negative k q squared over d squared, that's our hypotenuse, times cosine of 60, and that's our x hat, plus, because this is going to be positive, k q squared over d squared times sine of 60 degrees. And that's our y hat component. So let's do it for Q3. So F3 onto 1. So we are in the positive x-axis. So the adjacent side is still the cosine, so I'm sorry, the x component. So q, or k q squared over d squared times cosine of 60 x hat. And this is also positive in the y, so plus k q squared over d squared times sine of 60 degrees. Hopefully you're getting a little bit excited right now, noticing that something's going to go away. These two are equal in opposite direction, so our x components are going to go to 0. Add them up, and they become 0. Our y components, then, are just 2 times this value. So the sum of the forces for F31 and F32, or we'll just call it the resultant to make life easy. Resultant vector is 2 times k q squared over d squared times sine of 60 degrees. Y hat. And do we have some values that we can give that? Okay, so I gave it some values. So D is 0.15 meters and Q is 17 times 10 to the negative 6, so microcoulombs. And it just so happens that cosine, or sine rather, is square root of 3 over 2. So let me rewrite this before we start putting in numbers. So 2, I'm going to put the sine of 60, square root of 3 over 2 times k q squared over d squared. So notice that simplifies. So this equals the square root of 3 times k q squared over d squared. So now we can put values in for that. I'll go ahead and put in this 17 microcoulombs, the 0.15 meters, and k as 9.0 times 10 to the 9th. Just making life easy. Let's see what we get. And I get that the resultant force is 200 newtons. And that kind of makes sense. They're all the same magnitude. So I'm going to have a repulsive force if I'm looking at this Q1 from Q2. It's going to push it this way. And from Q3, it's going to be equal and opposite. It's going to push it this way. So these magnitudes, these two vectors here, are going to be equal in magnitude, opposite in direction. So that would mean that my resultant is going to come straight up the y-axis, which is what did happen. And that gives us this 200 Newton force. We don't have the magnitude until we look at it and say, well, it's one number, so if I square it and take the square root, then it's going to be the same darn number. So actually we do have the magnitude. And it's going to be straight up. Cool. What's happening at our other points, though? Well, if this is bisecting, and you kind of rotate this, that means that because everything here is equal and opposite, if I draw a line through here, we see that this is 30 degrees now, and this is 30 degrees. And the same thing is going to happen on the other side. So I'm going to have the same charge, or same force, but coming down 30 degrees below the negative x-axis over here, and over here I'm going to have 30 degrees below the positive y-axis. So see, it started off looking frightening, but it simplified pretty nice because everything kind of canceled each other out, and when we have everything equivalent, then we know what's going on the other side. It's just a matter of then figuring out what the angle is going to be between the two. So we didn't get to use our tangent, but don't worry, I will come up with examples where we do, and I will see you tomorrow.